Well, I'm going to kind of leave it at there, and I'm going to talk about just the methods we use to evaluate these limits. They're mostly the same as the methods you see elsewhere, with one big difference.
So what if it oscillates?
Well, that's a good question. So, if it oscillates, does it oscillate with a constant amplitude or not?
No, decreasing.
Then it can go to zero. Then it can go to zero, sure. You can have, for instance, so I assume you're talking something like this, Chris, right?
Yeah.
Yeah, then the limit's going to be zero, for sure.
What if it doesn't have a decreasing oscillation?
Then the limit doesn't exist. It's divergent. Which gets to the point that I was trying to explain a couple classes ago. Divergent can mean more than one thing.
Right.
So divergent can mean it goes to infinity, but it also can mean, like if you look at the limit as x goes to infinity, the sine function, it never goes to infinity, but it never makes up its mind either. Right? So there's different levels of divergence that come into play. Although we lump them all together and just call it divergent. We don't have names to specify the distinction between the two. All right, so here's the theorem. Very easy theorem. This is a theorem that says if you simply replace your n's with x's and evaluate the limit in terms of x, whatever you get out of that is the same as the series, the sequence, you know, the thing that you had. So in fact, let me use an example like this to illustrate it.
And this applies where?
Well, I'm going to get to that. There are several catches to it in the sense that you can't always replace your n's with x's. And let me give you a for instance there, Jessica. So if you had something like this, can anybody tell me what the limit of that sequence is? It is very much equal to
Zero.
Yeah, zero. N factorial is one of the quickest growing functions in mathematics. In fact, it's one of the few that actually beats out an exponential. Factorials grow faster than exponentials. So if you divide by a factorial, obviously it's going to get very small very quick. There are ways to justify that, but the problem is you can't just invoke this theorem. You can't simply make an argument based upon this. And why can't you do that?
Factorials aren't defined for
Right.
decimals.
So you see the distinction here, Jessica, is the x is a real value, and this is a natural number.
Okay.
Now, the comment I made here, whenever the function and the general, or the generator for the series are equal whenever x and n are the same, but realize that the series is not defined for fractional values, you know, of inputs, like the function is. So, for instance, if we had, let me pull one from the book. Hold on a second. Yeah, here's one. This is one you can probably look at and give me the answer for. Just hold off on it for a second. Do you see in this case, Jessica, there's no problem with simply replacing the n's with x's? It's a well-defined function. You don't have any factorials or anything going on like that. You know, another problem that arises is terms like this. What would be the problem with me writing that? What could possibly arise that causes an issue? Well, since x can be anything, can it equal something like a half or a fourth or a sixth? what's the problem with a half or a fourth or a sixth?
Imaginary.
Imaginary, right? So there are these issues that kind of
Imaginary.
arise, whether it's a factorial or something with an exponent like -1 raised to the power. See, in that case, I can't simply swap all the n's for x's, all right? And then we need to use another technique. But in a case like this, it works just fine. Who can help me actually evaluate that? What was
Is
it?
it
5.
Well, 5, yeah.
Yeah,
But
it's 5. So what would the
L'Hopital's
technique be?
LHR.
Yeah, you use L'Hopital's rule. Or you could also, if you go way, way back, old school style, like from the first semester of calculus we did together, divide through by the highest order exponent. So. But you're right, Christian, an application, 2 applications of L'Hopital's rule works just fine. Right, so from that, according to the theorem, what we can say is that the limiting value of the sequence itself goes to 5. Very simple theorem, right? If you're, in other words, if you're able to swap your n's for your x's, if you don't have one of these special cases arising, then just go ahead and do it. Evaluate it in terms of x. Whatever you get out of that for the limiting value is going to be the same as the limiting value of the sequence.
I just realized that'd be a really hard function to see.
To see.
If you're just looking at the numbers, the sequence.
Oh, yeah, absolutely. I'm sorry, too, because you're right. Some of these are very, very hard to see. I mean, the homework problems you'll encounter with the pattern. So what Christian's saying, guys, is if I just listed out the numbers to that sequence, the chances of you identifying it like we identified these are close to 0. Because, I mean, to come up with a formula like that off the top of your head is nearly impossible. And in fact, they have software that kind of helps in that process, you know, for when you do need to identify these more complicated patterns.
So, some of the homework is just gonna be us trying to figure out what this sequence, or what the,
Some of the problems, yeah, some of the problems, just like what I erased, they're gonna give you a list of numbers
and
and
then
say,
the other ones are gonna be like that?
yep, find the limit. Yeah. And so really, the problems are gonna be one of 2 varieties, either find the generating sequence or find the limit, but when you look at the problems under find the limit, there could be one of any number of ways that you accomplish that.
Right.
You know what I mean? Like here, I can trade the n's for x's, and there's no difficulty behind it. In other problems, like if you had a factorial, you got to use this bounded and monotonic theorem I'm going to talk about in a little bit. Another thing that we can use here is what's known as, well, you guys probably know this already. All I'm going to do is readapt this for sequences. But it's the same squeeze theorem we saw for continuous functions. Technically, it would be equal. One of the differences in this version of the squeeze theorem you see is this comment for all n greater than some capital N, that says some definite value. Let me draw a picture to illustrate this. This is something which is going to arise quite frequently when it comes to series and sequence.